Welcome to lecture 5 of video course on Tribology. The topic of this lecture is friction instability. It's a very interesting topic. Friction causing instability or causing instable system, introducing some sort of disturbance, some sort of continuous vibration phenomena or jerk phenomena. We will be studying in this topic detail of why friction instability happens and how we can avoid it. To start with that, we will take one example related to our previous lectures, and the example as I am shown in the slide says that determine coefficient of friction between two smooth surfaces. So, when we are using the word smooth surface, that means surface roughness is negligible, or in other word, coefficient of friction due to employing effect will be negligible. We can neglect that and we can consider only coefficient of friction due to adhesion or junction growth. Here we have defined the two surfaces, one is made of aluminum, another is made of steel. Three conditions have been defined: the dry, oily and semi-solid lubricated. Solid lubricated may be in this case we can say there is a powder lubrication, molybdenum disulfide or some Teflon related coating on that. In addition to this data, shear strength of steel is given, that is a 300 megapascal, and shear strength of aluminum is defined as 100 megapascal. So, aluminum will govern the behavior of this tribo pair. As we have learned, shear strength of weak material need to be accounted. So, we can say the shear strength of aluminum will be considered, that will be 100 megapascal, and shear strength of steel, which is defined as a 300 megapascal, will not be utilized for our expressions. Then in addition to this, we have data related to interface shear strength, which is a 2 megapascal, 0.150 megapascal, 0.05 megapascal, and the dry, solid lubricated and oil lubricated condition. From this example, it is clear that oil lubricated condition will give minimum shear strength of the interface, and dry contact will give the maximum shear strength of the interface. So, we can utilize formula which we derived in a previous lecture, that mu due to adhesion or junction growth is equal to 0.5 divided by square root of the ratio of shear strength of weaker material to shear strength of interface. As we have mentioned in previous lecture, we discussed in previous lecture that this ratio decides what will be the coefficient of friction. It is not an absolute material shear strength which decide, but the ratio of interface shear strength to bulk shear strength of material is going to decide what will be the overall shear coefficient of friction due to junction growth. If I take this ratio, the tau y by tau I, that means 100 megapascal divided by 2 megapascal. So, that gives me 50 value. That means, this ratio tau y by tau I for solid for dry condition is 50, and this ratio for solid lubricated surface is 667. Not very different, not very much different in this case, and while for all lubricated case is turning out to be 2000. Using this ratio value, we can find our coefficient of friction is turned out to be 0.01 for dry case, 0.0075 for solid lubricated case, and 0.0025 for all lubricated case. I can interpret these results in three ways. First thing is that dry lubrication gives a high coefficient of friction, and Second thing is that getting coefficient of friction equal to 0.00075 does not mean much. It will not really waste much power. So, these are the hypothetical values. Third interpretation can come that as the coefficient of friction is very low, I can choose even the dry contact. If I go through overall economic point of view, if I consider the cost of a lubrication, mechanism of lubrication and accessories which are required for the lubrication mechanisms, I can reject second and third option. I can say that 0.01 is coefficient of friction is very, very low. We can go tolerate this, we can go ahead with this. But there is a problem. Problem is that whenever there is a dry lubrication case, there will be more variation in a static coefficient of friction and kinetic coefficient of friction that will bring or that will induce instability. That is what we are going to describe in today's lecture, we are going to discuss in today's lecture. So, we can say friction induced vibration is an instability or vibration, we are using the word. This is coming because of the static and kinetic friction coefficient or difference between static and kinetic friction coefficients, and this difference is initiating stick slip process. How? We are saying that anytime velocity of the object or instantaneous velocity of the object does not remain close to the average velocity, that means there is a continuous fluctuation in velocity, sometimes it is moving at a higher speed compared to mean speed, sometimes a lower speed, and that kind of variation in velocity will introduce vibration phenomena. And if vibration phenomena have some lack in the damping, then instability is bound to come. These phenomena are often known as the shock phenomena, but we are trying to get a feel from that. Sometimes material is in a contact and sometimes it is not there. So, there is a continuous jump phenomena, shock phenomena which is keep going on as one surface moves related to other surface. And this is very, very common in the braking, or we say the brake shoe and disc, brake shoe and drum. This is a very common phenomenon. That is why the noise gets induced when we apply brake. Due to variation in velocity, wheel is suddenly getting slipped, and that is why the noise comes, chirpy noise comes, which is many times intolerable. That is why when we design good brakes, we try to keep this in our mind. This kind of noise should not be there, or if it is there, it should be at very, very low level. We try to design brake and brake material from that angle, that minimum noise should be generated when we are applying brake, when we are trying to stop vehicle or we are trying to stop wheel. It largely depends the rate of the friction force, at which rate friction force is applied. Is it applied very fast? Is it applied gradually? That decides whether there will be friction instability or not. To elaborate this, I am just showing a couple of results which we have done experiments on one brake material. What we use a brake material as a magnetorheological liquid as a brake material. Good thing about MR fluid or magnetorheological fluid is it gets solidified in just a few milliseconds, and due to this solidification, coefficient of friction will increase significantly. We say coefficient of friction from 0.1, it can reach to 0.6 in 10 millisecond, which gives a braking torque, or which give the resistance against a movement. But what is the problem with this? So, when we used when we perform experiment on MR brake, what we got at the lowest speed, coefficient of friction was very high, our torque resistance capacity of that brake was very high. You can say that here the blue line, pink line, yellow line and the green line. What we are showing here, the blue line is for 0 ampere, that means there is no magnetic field generated in MR brake. While at the point 2, some magnetic field was generated, which churned up the liquid, converted liquid particulated liquid to some semi-solid, low shear strength semi-solid. When you apply current 0.4 ampere, it turned out to be moderate level, and 0.6 ampere it was very high and a good torque resistance capabilities. You can see the torque capabilities at the 0.6 ampere of that MR brake was almost 75 Newton meter at a negligible speed. But as speed is increasing, the rotational speed where the brake was applied increases, we are able to see that there is a continuous decrease in torque or resistant torque offered by the brake. It reaches to the minimum value at some speed. In here it is shown around roughly 250 to 60 rpm. It shows the minimum value, and after that it reaches to the steady value. After there is a 400 onward fluctuation are negligible. So, it is a problem. There is particularly when operating speed is nearby 260, may say within a range from 200 to 300, there is a possibility of friction instability. Coefficient of friction does not remain stable. It keeps changing from one value to other value, and that is dangerous. That makes a lot of noise, which should be avoided as far as possible. And in this case particularly, if we are operating at the brake at the lower than this speed, very high coefficient of friction and maybe quite possible a jerky motion comes and stops vehicle immediately, which is also should be avoided. Which is we should try to apply this kind of brakes when speed of operation is more than 400 rpm. Lesser than that, these brakes are not showing the very good performance, and it need to be supplemented with some other brake materials. What we say, the observation from this slide is that coefficient of friction decreases as the velocity increases, but there is a limit. It is not continuously keep going down and continuously decreasing. It is reaching to one steady state condition. And if I remember kinetic coefficient of friction and static coefficient of friction, we say that static coefficient of friction we can calculate at the first point at just the start, and kinetic coefficient of friction when it comes reach to the steady state condition. But difference in that coefficient of friction is almost 6 to 8 times. We say that coefficient of friction at the static level is suppose 0.8, and kinetic coefficient of friction turn out to be 0.1. And whenever there is a large difference between static coefficient of friction and kinetic coefficient of friction, there is a possibility of friction instability. We will drive mathematical equation and try to find out how this variation is affecting the result. But before coming to that, I have some more examples available from the literature. So, this figure shows coefficient of friction variation. This says that even the sliding speed, with increase in sliding speed, the coefficient of friction is increasing, which is amazing. We never feel during the experiment that this happens, but it turned out to be this is a micro or nano level study which was performed on the lead block versus steel and indium block versus steel. Shows that when you are pushing one block on other block, even though applied force is lesser than static friction force, there will be some micro slip. That is why the speed is shown here in 10 to minus 9 mm per second, which is very low, negligible. We cannot be detecting by naked eyes. In that case, coefficient of friction is continuously increasing. Ideally, we believe that coefficient of friction remains stationary or static value or the start, because we are not able to detect this so low velocity in common experiments which we perform in the lab. And after a certain speed, it reaches to static condition, and after that there is a decrease. So, this micro sliding really, if it is required in micro machines, we need to consider the how velocity is affecting coefficient of friction, and this just opposite. The Coulomb said clearly coefficient of friction does not depend on sliding speed, but this kind of micro experiments, they are experiment which performed on micro scale, they clearly show that coefficient of friction depends on velocity. And of course, we know that static coefficient friction and kinetic coefficient of friction, we are taking only 2-point value, but there will be some gradual change. It cannot that static coefficient of friction is 0.5 and suddenly it reaches to 0.2. It will not be 2 point, it will be some linear curve or some parabolic or some exponential curve. which need to be accounted when we talk about the friction instability, when we want to operate the machine in that zone or in that domain. Now, why this kind of phenomena really happens? Couple of hypotheses are there which say that interlocking of asperities during stiff slip phenomena. If the operating speed is low, what will happen? We push block, asperities are in a contact. After some resistance, block will start sliding. It will climb up on some asperities, but after that again it will come down. Then there will be lesser coefficient of friction. Then again some asperities will come, again it will climb up, coefficient of friction again will vary. So, if we apply once force, after that we do not apply force, when we push block, it will climb up, it reaches to static condition and we leave it, the block will not stop there, it will move down to some value and then slowly it will come to stationary. In other words, what we are saying that when we are applying force and it is overcoming static coefficient of friction or static force, then it will be having lesser kinetic force plus some inertia plus some velocity to that block. We will come to that when we study or when we describe the mathematical relation. A similar phenomena will occur when there is adhesion or adhesive component, or the two components are getting welded at asperities. When you push it and leave it, what will happen? The junction will be broken or sheared, and after some again they will be formed. And last is the electrostatic charges. There is a molecular attraction and they may not be making cold junction, but they have attraction force that will broken and again reform, again broken and again reform. These three mechanisms can describe why strict slip phenomena happens if we are trying to operate machine in very low speed domain. If you are operating machine at the very high speed domain, some other instability comes, then in that case friction instability does not come, but the low speed operation friction instability is dominated and we need to cure it, we need to avoid it either using active control system or some lubrication mechanism. You say that to avoid this phenomena, either increase operating speed, that means if I want to operate the machine at the 100 RPM, I should redesign in such a manner the operating speed is going beyond 100 RPM or maybe it's reaching to 150 or 175, and we need to redesign the system in such a manner. New design is avoiding the friction instability in every sense. And other way is that try to reduce mu s and mu k. Maybe you make you choose a tribo pair which have a lower difference between a static coefficient of friction and kinetic coefficient of friction. Change material or you introduce some lubricant, because in introduction of lubricant or forced lubrication will reduce this coefficient of friction and difference between the static coefficient of friction and kinetic coefficient of friction. I can give a very typical example of journal bearing. When journal bearing, particularly under radial load, operates in the fully developed condition, coefficient of friction is very low, maybe say 0.001. But when it is during start and stop, if there are no friction modifier available, then starting coefficient of friction will be very high, it may be in the 0.1, 0.15. So, difference in a static coefficient of friction is a 0.1 or maybe say ranging between 0.1 to 1.15. While we are coming to the fully developed aerodynamic bearing or fully developed journal bearing, coefficient of friction is reduced to 0.001. The huge difference between static coefficient of friction and kinetic coefficient of friction. And if you want to operate really that journal bearing or aerodynamic bearing at the lower speed operation, surely there will be contact, no contact, contact, no contact, contact, no contact. There will be jump phenomena, there will be continuous variation in a position of the shaft. So, we try to avoid it. To give a slightly more detail about this, we will take one example. We say assume there is an assembly and there is a block. Block has a mass m. Artificially we are assuming there is some sort of viscous damper and there is some spring stiffness. Spring and damper are connected to assembly. Or in other words, when we are pushing this block related to the stationary surface, this force will be constrained due to the stiffness and damping force. which is a very common machine element, or is almost all machine element have this kind of a stiffness and damping coefficient. Damping coefficient can be very low, can be high, depends on how the system is arranged. We are talking about the viscous damping, we can replace for simplicity with the Coulomb damping. Expressions will remain same, or it can be interpreted in that way. Now, we are saying that unbalance will come if there is a difference between a static coefficient of friction and dynamic coefficient of friction or kinetic coefficient of friction. What will happen? There will be balance force. We have supplied friction force equal to static force, which is really required to start sliding of the block. Once sliding start, then friction resistance is coming down, is reduced. This will give us unbalanced force. That unbalanced force will initiate acceleration, will induce acceleration in the block. As there is acceleration, naturally velocity will increase till balance force is nullified. Once it happens, there is a possibility of sticking, and that is why we say that eventually block M will come to the rest, mass M will come to the rest. If I plot displacement, velocity and acceleration diagrams, what we get? You can see this displacement is coming increasing to a certain value, where the equilibrium force is forcing block to be at some position away from its initial position. And see the velocity, you are able to see the velocity reaches to a peak value and then drops back. While acceleration start building, I am just taking this point as an initial push given to the block, and after that when it is started sliding, then acceleration is going up to a certain level and then again decreasing or going to the negative side and finally coming to the rest. So, this kind of behavior is observed when we push block right to the one surface and stop supplying force. We give force equal to force required to start sliding the block. And as we have attached one viscous damper and stiffness, we can say overall behavior of this stick slip behavior of the system depends on the system stiffness and system damping, and the difference between force required for sliding and force required for continuous sliding. So, overall performance will depend on this. Now, to elaborate this kind of behavior, we can take simple example of very simple example. In this case, we are saying that the x direction is sliding speed and y direction there is a friction force. Fs and Fc is shown over here. Fs is a static coefficient of Fx is a static friction force. Fc is a force required for sliding or continuous sliding or when block started sliding. We can consider two cases. This is the first case when we are assuming ideal case. Initially, there is a high static coefficient of friction that makes high friction force, and then subsequently there is a lesser friction force. So, that is why there is an abrupt change. We have supply more, then it comes to the 0 and not 0, it is equal to F c and that continues. This is ideal case, and that is why we are saying that this is the only stiction. Immediately the junction are broken and the block starts sliding. While we can consider other case where static force is initially Fs and reaching slowly to the kinetic friction force. That means, there is a linear profile, it is not immediate, it is a linearly varying from initially high value to some certain Fc value, and there is decrease, and we do a reverse operation and the same thing is going to happen when we do the reverse side loading. we can consider this case. This is the ideal case, it does not show any problem, but we can consider this case which will show under which condition system will be unstable or friction will induce instability. To consider this in right manner, we will start with a common equation which we generally use for the damped vibration. We know this is a second order equation or partial differential equation can be said, but here we are using only x, we are taking only the one direction. So, it can be converted in differential equation. M is a mass, C is a damping force, large viscous damping force, and K is a system stiffness or a stiffness which is attaching the block. We can non-dimensionalize it, so that we can interpret it in much better manner. We say there is a damping factor which is a ratio of damping coefficient divided by critical damping. Natural frequency is a ratio the square root of ratio of K by M, that stiffness by mass. When we use this expression, we can rearrange this first equation to this equation. Now, we know the solutions are available for this kind of equation, and they are categorized in 3 categories: case 1, case 2, case 3, based on what is the value of zeta. It is zeta lesser than 1, that is known as the under damped system, and solution or for x is generally in terms of t is given as some constant exponential decay in the magnitude, and then trigonometry terms. We can write in terms of sine plus cos, or here we have written some phase angle, so that we can express either in the sine or in cos term. Case 2 is over damped with the zeta is greater than 1. Here we can see exponentially both the terms are going to be negative side. So, this will be continuous decay, this will be continuous decay. And the third case when zeta is equal to 1, that is the boundary case, we are able to see that this it will take one period time to stop the vibration. If we disturb any block, any system, any component, it will come to the rest after one period, one complete cycle. While in case of the over damp, it does not show that there is a possible that it will be damped immediately without taking much time, or it may take slightly longer time, or magnitudes may be slightly longer time depending on the overall characteristics. While in the first case shows that clearly there is a sinusoidal term, there is a periodic term, that means it will keep going, getting some oscillation, but at the lesser and lesser magnitude. There will be reduction in amplitude of initial disturbance, but it will continue over the number of cycles. We generally use a logarithmic decrement expression to find out what is going to happen to this system. Now, in this case particularly, zeta is important parameter for us, shows that always zeta is positive. We are not consider here zeta as a negative, we are not consider negative damping at all, but there is a possibility of negative damping, even though physics does not permit us to say what is the negative damping, how heat generation, how energy generation will happen without any input, but mathematically we can interpret it and we can show why the friction instability occurs. Just to elaborate that, what I am saying that there are two cases. One is a positive damping, there is another case the negative damping, and in both the case displacement is shown on the vertical x, y x, and time is shown on horizontal x. When the damping is positive, you can see even the amplitude is initially high, and of course, in this both the cases we are considering under damped when the zeta is lesser than 1, right, and in this case zeta is lesser than 0 even. So, positive damping zeta is lesser than 1 is a under damped condition, the coefficient displacement goes on a maximum value, comes back to minimum value in the negative side and opposite side. Then next cycle it goes again to high value, but lower than first cycle damping, and we are assuming this is a natural damping, it is not a forced damping system. and it keeps going on, and finally it reaches to some stationary condition, and if this 0 is the initial condition, it will reach to 0 condition. Well, coming to the negative damping, even though it is start from the 0, it reaches to the some max value, then in next cycle this value increases, and subsequently this value keep on increasing till a final knock between the component occurs, or impact between two component occurs, or shock between two component occurs, which will make a lot of noise, which will reduce the life of component and may cause a fracture of the component. If you say that cast iron shaft, cast iron block is there, and we are using some ceramic component against the cast iron, and we experience the negative damping, naturally cast iron will break, or ceramic block will break, because they have a low fracture toughness, and failure will occur. So, that is why we should avoid this kind of negative damping as far as possible, otherwise we need to redesign a system so that this can be avoided. To consider this further in detail, let us take a force damp vibration case. This is the same as we have described in earlier case, except the last term, or the right hand side term, which is shows the external force as a function of time. This force is varying with the time. Here we are trying to consider F as a friction force. When we consider friction force, naturally a negative term will negative sign need to be included in this case. This is not making the motion, it is a resisting motion. We know the friction force resists the motion, that is why the negative sign has been introduced over here, and we need to find out the expression for F of how the friction force is varying with the time. We initially consider two cases when the friction force was immediate changing from one position to another position, changing from Fs to Fc. In this case, we are assuming that there is some sort of linear profile, it changes gradually. It is not immediately happening from Fs to Fc. To accept that profile, we can say Ft is a function of Fs is a stationary force, or is a force required for the just initiating slide, minus some lambda, some parameter, and velocity, right, which is reasonably good for us to understand. From this angle, we know that as the velocity is increasing or velocity is decreasing, how the friction force will vary, and once we know that, we can find out whether there will be any effect of this force on vibration phenomena of system or not. That will be helpful to us. Now, we introduce this, we say that in this equation we instead of writing Ft force function as a function of time, we have written Fs minus lambda dx by dt. We can rearrange this equation, keeping Fs on right hand side and clubbing dx term with a dx term, which is c minus lambda dx by dt. So, this will give us equation now. We can find out the answers for this. Here M is a block to be moved against the stationary surface. This is the acceleration term, which if initially disturbed, how long this term will remain and what will be magnitude of that, and we assume the initial disturbance force or the disturbing force is Fs, or maybe continuously we are applying of this force Fs. What will happen during the what kind of motion will occur and how result will affect. Here the stiffness is also accounted. Many times we find difficulty in estimating the stiffness. So, what we do, we write equation, we find out the solution, and based on some parameter, some fraction, we can use scaling factor or correction factor like alpha, beta, gamma, introduce those factor to get a continuous reliable results. In other words, we do first theoretical calculation, so evaluate the expression, try to match with the experimental results, find out some correlation parameters, and subsequent to that we try to get the results matching for the subsequent experiments. That means, first few experiments will give us those parameters, and subsequent to that, whatever we do experimentally, we should be able to estimate directly from the expression that it will or ultimately that is going to reduce the number of experiments, it is going to help us, right. So, in this case is that if the system damping is low, think over, the system damping C is a lesser than lambda. There is a possibility the system damping is lesser than lambda. Many times we do not have damping available, or materials are not able to damp vibration, and decrement in friction force is significant, that means lambda is much larger than C. So, in that case what will happen is this will turn out to be negative. If this turn out to be negative, that is going to initiate sliding, or in this is going to initiate instability or introduce instability in sliding operation. So, if I revise or think over back to the expression, what we are going to get is x is equal to some constant e power zeta omega n as a natural frequency in time. We are trying to find out what will be the effect on a magnitude with the time, and this is periodic term, that is a sine term with some phase angle. Zeta here we are assuming lesser than 1 at may overall expression. Now, if this zeta is decided based on this C minus lambda divide by 2 square root 2 under square m into k. M is not going to change, k is not going to change, C is not going to change, it is only the lambda which decides, and that is depending on the how steady coefficient of friction is getting or converging to the kinetic coefficient of friction. If there is a huge variation, the steady coefficient of friction is maybe say 0.3, 0.4, and kinetic coefficient of friction turn out to be 0.05 or 0.1, there is a huge difference. Naturally, there will be a good value or finite value of the lambda which may be more than or greater than this C. That is going to introduce instability. That is a major problem for us. So, we should look at in that, and we try to avoid at least if we are able to see this expression, if we are able to find out C of the system using model analysis or some other technique, and we are able to estimate the behavior of friction pair, where static friction force has been plotted with a velocity, and we find that there is a large variation, and whatever the operating domain we have, operating speed we have, we require, if in that case the lambda value is very high, then we should avoid it. So, with this I believe that you are getting a feel of how coefficient of friction is important for us, or why we want to keep this gap to a minimum value, so that results are favorable to us and we can avoid instability. As mentioned clearly in our earlier slides, that if the zeta value is lesser than 1, then there will be periodic motion, and this zeta value turn out to be negative as was indicated in earlier slides, then there will be instability, and there will be knock, and there will be a noise generation, and that will cause some problem to us. Now, this is what we are showing over here. If I take a very small variation in C and lambda, I am assuming that lambda is almost reaching to the C value, slightly more than C value. You can see the friction instability. Here it is going up first, coming down, and maybe this data is missing here, that is why the straight line is coming over here. So, if I get intermediate data, some data will come over somewhere here, that will increase magnitude to some level, and that shows that first displacement is a certain unit, means a 0.65, 0.64, and if this missing data is can be collected back, it will go slightly more than that, and further slightly more than that, right. So, magnitude is changing slowly, and before that we halt the operation or able to overcome this, then system will remain stable, will not make much noise. But if you are not able to control on that, then system is going to make a lot of noise, is going to hamper the operation or lose its main function. So, we can say that increase the system damping is one of the possible solution, increase the value of C itself. If you do not have much control on the friction or friction pair, or I am not able to provide lubricant because of one reason or because of some other reason. Like many times we are not able to give a lubricant to the machine related to textile operation, because we know the textiles will get affected with lubricant and it should be avoided. However, if it is possible that we can lubricate the surface, then it will be always preferable go ahead with the lubrication and ensure that friction force difference between static coefficient of friction and kinetic coefficient of friction is decreased. This is the reason why when we are mentioning about I have given example of hydrodynamic bearing. In hydrodynamic bearing, I mentioned that at a staff coefficient of friction may be very low, 0.1 to 0.15, and when we are operating it at the fully developed condition, coefficient of friction may be 0.001. There is a huge difference. If we operate that machine at a very low speed, naturally we are going to face problem. There will be more wear, there will be more knocking of the shaft versus shaft over the bearing surface. But if we are able to provide some other mean to separate shaft and bearing initially, which happens many times, we use a hydrostatic lubrication mechanism. We provide lubricant to separate two surfaces and then start shaft rotation. Otherwise, there is a more possibility of failure or more possibility of knocking, more possibility of noise. To avoid that, we do that. Sometime even in hydrodynamic bearing, we use a magnetic levitation mechanism, that we use a permanent magnet at the start or where the shaft surface is going to touch a bearing surface. We use a magnet piece there, or maybe say some short arc, maybe 30 degree to 60 degree to levitate the shaft slightly up, so that there is no contact, and when the shaft will start rotating, it will develop a full film lubrication mechanism, and coefficient of friction will be almost same, 0.001 at the starting, 0.001 at the later operation, maybe slightly more than that. So, that kind of mechanisms are important. When we understand what is really happening in a system, we can avoid it. So, I have given a couple of example on how to avoid the friction instability in bearings. Similarly, we will detail this kind of topic, and when we will design brake system, how to design a brake system, how to avoid the squealing or noising or slippage of brake shoe against the disc. So, we will continue with we will stop over here on the friction topic. We will be starting a new topic on the next turn, that will be the wear phenomena or wear mechanisms. Those will be different operations. Thank you for your attention.